Sections 11.2 through 11.4 deal with matrices, which is a way to organize systems of equations. So this is an example of a matrix. It's a rectangular array of numbers. These are the rows, these are the columns. We label the size of a matrix, the rows by the columns. So this would be a 4 by 5 matrix, 4 rows by 5 columns. Each number inside the matrix is called an entry, and we also name the entries by the row by column. So E sub ij is the value in row I, column j. For instance, E2, 3 would be the one that is in row 2, column 3, so that would be 26. An augmented matrix we use to represent systems of equations. So if we have this system of equations down here, when we want to write the augmented matrix, we just drop the x and y. We let each column represent a specific variable. So for this example here, we let the first column represent the coefficients of x's, the second column represent the coefficients of y's. This bar represents your equal sign, and these are your constants. So then the first row represents your first equation, the second row represents your second equation, and if you had more equations or more variables, you would have more rows or more columns. A determinant represents the physical area spanned by a system of equations in a plane. We represent a determinant with straight bars as opposed to the brackets, so whenever you see these straight bars, you need to know that means take a determinant. You can only take determinants of square matrices, so a 2 by 2 matrix. The way you take the determinant of a 2 by 2 matrix is you multiply down from the upper left to the bottom right, so you have A times D, and then you subtract multiplying up from the bottom left to the upper right. So then you have minus C times B. So when you're taking a determinant, you should end up with just a single number. Okay. So go ahead and pause the video and try taking the determinant of this 2 by 2 matrix. So you should end up multiplying down 3 times 1 and then subtract off multiplying up 6 times negative 2. So you end up with 3 minus a negative 12 or a positive 15. In this class, we only go up to 3 by 3 matrices for determinants, and so there's a shortcut for these. So this is going to be slightly different than the way the book does it or the way that you would have to do it if you had a larger matrix. The idea is the same as for a 2 by 2 matrix, but your first step is to take these first two columns and to rewrite them to the right of your matrix. So you take these first two columns and you rewrite them over, okay, and then you're going to multiply down and then subtract multiplying up, just like we did for the 2 by 2 matrix, but now there's more down rows, diagonals, and more up diagonals. So you add them together. So you're going to multiply this first down diagonal starting in the upper left corner, so 2 times 5 times negative 9. Then you're going to add the next down diagonal. You have negative 1 times 0, and then you're going to add the last down diagonal. So you have negative 3 times negative 2 times 6. So now we've done all the down diagonals. Now just like the 2 by 2, you're going to subtract the up diagonals. But just like on the downs, instead of just having one diagonal, there's actually 3. So you should end up with 0 times 5 times 3, 6 times 1 times 2, negative 9 times negative 2 times negative 1, all added together. So if you simplify, you end up with negative 90 plus 0 plus negative 36 minus 0 plus 12 plus negative 18, which ends up being negative 120. So go ahead and pause the video and try taking the determinant of this 3 by 3 matrix. So you should end up with 3 times 4 times 1 plus negative 9 times 0 times 8 plus 0 times 1 times negative 3 minus 8 times 4 times 0 plus negative 3 times 0 times 3 plus 1 times negative 9. What you'll find when you're taking determinants is you love when there's zeros in the matrix. So anything with a 0 ends up just being 0. So you end up with 12 minus a negative 9, which is 21. One way that we use determinants is something called Kramers Rule, which is using determinants to help us solve a system of equations. So if you have an augmented matrix here, then the x-coordinate is the determinant with respect to x divided by the regular determinant. The y-coordinate is the same thing with y, the z-coordinate is the same thing with z. What I mean by the determinant with respect to x is we're going to replace the x column with the answers and take the determinant of the 3 by 3. When I say just the regular determinant, I mean dropping off the answer column and taking the determinant of just the coefficients. So first thing, pause the video and write the augmented matrix for this system down here. So you should end up with 2, -4, -2, 3, 2, and 3. So now when we take the determinant with respect to x, we're going to drop off the x column and replace them with the answers. So we're going to take the determinant of the matrix -2, -4, 3, 2. So we took this x column, we got rid of it, and replaced it with the answer column instead. So go ahead and pause the video and take this determinant. So you should end up with a -4 minus a -12 or a +8. So go ahead and pause the video and try to do the same thing with the d sub y. So keep your x column the same, but replace your y column with the answers and take the determinant of that. So you should be taking the determinant of the matrix 2, -2, 3, 3. You kept the x column the same, and you're replacing the y column with the answers. So if you haven't already done so, go ahead and pause the video and take the determinant of this matrix. So you should end up with 6 minus a -6 or a +12. So then the last determinant we have to take is the determinant of just the coefficient matrix. So you're just going to drop off the answer column. You're not going to replace anything at all. So then go ahead and pause the video and take the determinant of just the coefficient matrix. So you should have ended up with 16, 4 minus a -12. So now your x coordinate is going to be your determinant with respect to x divided by your coefficient determinant. So you're going to have 8 divided by 16. So your x coordinate is 1/2. So now go ahead and pause the video and find your y coordinate. So you should end up with an x coordinate of 1/2 and a y coordinate of 12/16 or 3/4. So you end up with the point 1/2, 3/4. The last part is going to be matrix algebra, so adding, multiplying, and solving in a different way. So here we have two matrices, A and B. And first I want you to write down the dimensions of A. So remember, we always label the dimensions as the row by the columns. So both A and B are 2 by 3 matrices. You have 2 rows and 3 columns. So now we can add matrices together. In order to add matrices together, they have to be the same dimensions. So since A and B are the same dimensions, we can just add them together, in which case you just add each entry. So for the first entry, first row, first column, you have a 2 in matrix A and you have a 3 in matrix B. So this first one is just going to be 2 plus 3. For the next one, you have a 0 in matrix A and a -2 in matrix B. So you're going to have a 0 plus a -2. And you simplify them. So this would be a 5, and this would be a -2. So go ahead and pause the video and finish the new matrix A plus B. So adding each entry, you should have the same dimensions as the original 2. So you end up with 5, -2, 4, 1, 5, -9. You can also multiply a matrix by a constant. So 2 times B would just be you multiply every single entry in matrix B by 2. So the matrix 2B would be 3 times 2 is 6, -2 times 4 is -2 times 2 is -4, 6 times 2 is 12, 0 times 2 is 0, -3 times 2 is -6, -4 times 2 is -8. So go ahead and pause the video and do 2B minus A. So you should end up with 6 minus 2 is 4, -4 minus 0 is -4, 12 minus -2 is 14, 0 minus 1 is -1, -6 minus 8 is -14, -8 minus a -5 is -3. So adding matrices, they have to be the same size, and then you just add each entry. You can also multiply by a constant, in which case you just multiply every entry by that constant. Multiplying matrices is a little bit more complex. First of all, you have to look at the dimensions. So, for instance, the dimension of sum A is m by r, and the dimension of sum B is r by n. The inside dimensions, when you write them in the order you're going to multiply them, have to be the same. So in this case, it would have an r and an r. So the columns of the first matrix is the same number as the rows of the second matrix. And then your answer matrix is going to be the outside. So if we look at A, or for this first part, A times B, matrix A is a 2 by 3 matrix, and we want to multiply it by matrix B, which is a 3 by 2 matrix. So first we have to look, are the inside dimensions the same? They are, so we can multiply them, and our answer is going to be a 2 by 2 matrix. So when you multiply matrices, you multiply row by column. So you're going to multiply each entry in the row by its corresponding entry in the column and add them together. So if I want to find the entry that's in row 1, column 1, I multiply row 1 of my first matrix by column 1 of my second matrix. So I'm going to have 2 times 1 plus 1 times 2 plus 3 times 3. So I just go in order. So I have 2 times 1 plus 1 times 2 plus 3 times 3. So my first entry is 2 plus 2 plus 9, which is 13. So now if I want to do first row, second column, I would multiply first row by second column. So I'm going to have 2 times 0 plus 1 times 1 plus 3 times 2. So I end up with a 7. So now if I want second row, first column, I'm going to multiply second row, first column. So go ahead and pause the video and find that entry. So you should end up with 1 times 1 is 1, negative 1 times 2 is negative 2, plus 0 times 3 is 0. So you end up with 1 minus 2, which is a negative 1. So go ahead and pause the video and find the last entry. So second row, second column, you're going to multiply second row by second column. So 1 times 0, negative 1 times 1, 0 times 2. Again, zeros are going to make it nice. You end up with just negative 1 times 1, which is negative 1. So now what if we want to go the other way? What if we want to multiply b times a? So go ahead and pause the video and figure out, using your dimensions, whether we can multiply b times a. So B is a 3 by 2 matrix and A is a 2 by 3 matrix. So your inside dimensions, the columns of the first one and the rows of the second one are the same. So we can multiply them. And your resulting matrix is going to be a 3 by 3. So go ahead and pause the video and find the matrix B times A. So now you're going to be looking at the rows of matrix B and the columns of matrix A. So for first row, first column, you're going to multiply first row, 1 and 0, times the first column, 2 and 1. So 1 times 2 is 2, 0 times 1 is 0, you end up with 2. For first row, second column, you're going to go first row, second column. So 1 times 1, 0 times negative 1, you end up with 1. So on and so forth, you should end up with 3, 5, 1, 6, 8, 1, 9. So the main point to note is that matrix multiplication is not commutative. We did b times a and a times b, and we did not get the same thing. So the last part we're going to talk about is identity and inverse matrices. So identity matrices are like your 1 of the multiplication world or 0 of your addition world. Anything times the identity matrix is just itself. So you have a square matrix, 3 by 3, 2 by 2. Starting in the upper left down to the bottom right, you have 1s. Everywhere else you have 0s. So this would be the identity matrix for a 3 by 3. So then an inverse matrix, just like we have an inverse in multiplication or addition, would be any matrix times its inverse is the identity. So we're only going to do inverses of 2 by 2 matrices. There's a shortcut. So here we have this matrix. So for a 2 by 2 matrix, the inverse is 1 divided by the determinant of the original matrix, and then you switch the upper left to bottom right, so it would be 1 and 3, and you make the bottom left to upper right the same but negative, so it would be negative 1 and negative 2. So the determinant of this matrix is 3 minus 1, so you end up with just a 1, so you get 1 over 1 times 1, negative 1, negative 2, 3, which is just the matrix 1, negative 1, negative 2, 3. So that is the inverse of matrix A. So using inverses to solve systems of equations, if you have an equation ax equals b and you want to solve for x, you would multiply both sides by the inverse of a, or we usually say divide by a, but it's the same thing. So we'd multiply both sides by the inverse of a, and then x is whatever that thing is, A inverse times B. Well, it's the same idea for matrices. So first, where A is the coefficient matrix and B is your answer matrix. So first, I just want you to write the matrices A and B. So A is the coefficient matrix, 3, negative 1, negative 2, 1, and B is your answer matrix. So now the first thing we need to do is find the inverse of matrix A. So go ahead and pause the video and find the inverse of matrix A. So the inverse is 1 over the determinant, in which case the determinant is 3 minus 2, which is just 1. And then upper left to bottom right, you switch those two, so it becomes 1 in the corner and 3 in the bottom. And then upper right and bottom left, you make those opposite signs, so it becomes 2 and 1. So then you end up with just the matrix 1, 1, 2, 3. So using what we know about algebra, x is equal to A inverse times B, where x is the xy matrix, A inverse is the inverse of the coefficient matrix, and B is your answer matrix. In this case, multiplication order matters because we're talking about matrices, so it has to be in this order, otherwise you won't be able to multiply them. So go ahead and pause the video and multiply these two matrices together. So we have a 2 by 2 matrix times a 2 by 1 matrix. Inside dimensions are the same. Our answer is going to be a 2 by 1 matrix, so we end up with 1 times 8, 4 is 12. 2, 3 times 8, 4 is 28. So x is 12 and y is 28. So our solution to our system is 12, 28. And this has been Matrices.